In this video, I will derive the discrete expression of the Fourier transform. An arbitrary function f of x can be expanded into an infinite series of complex functions in this form. The sum of a sub n times e to the power of I n x. I is the square root of -1. N is an integer from -infinity to positive infinity. We will now derive the expression of a sub n. First, we multiply both sides by e to the power of -I m x, and then we integrate these two sides. We get this equation. The key is to evaluate this integral, and we will prove that if n is different from m, this integral equals 0. Therefore, this infinite series will be reduced to simply one term, a sub m times the integral of e to the power of 0x dx. Now let's prove this. When n is different from m, we have the integral of this exponential function from -pi to pi, and then the indefinite integral of this exponential function is itself divided by a constant. We plug in the values of pi and -pi. Remember this. Euler formula tells us e to the power of I theta is cosine theta plus I sine theta. And then we can see the two cosine functions cancel because cosine functions are even functions. Sine functions are odd functions. They do not cancel. We get 2i times sine n minus m times x. However, because n minus m is an integer, sine functions of an integer multiple of pi or -pi is simply 0. We just proved that this integral is 0 if n is different from m. What if n equals m? In that case, this part becomes e to the power of 0x, which is just 1, and this integral is simply 2 pi. And then by using these two expressions of this integral, we see this, the left-hand side, over here, the left-hand side, equals only one term, 2 pi times a sub m. Now we have the expression of a sub m, which is just 1 over 2 pi times this integral. Therefore, if we know the expression of f, we plug it in, we evaluate this integral, and then we have the coefficient here. And because m or n is a dummy variable here, we do the sum. So we can simply say a sub n equals 1 over 2 pi times this integral. And now we have fx equals 1 over 2 pi times the summation of this integral in blue times e to the power of I n x. And this part is simply the discrete expression of the Fourier transform of fx, the blue part. Now I'm going to give you a few examples. Example 1. Fx is equal to sine x. How do we determine this expression? Simple. A sub n is just 1 over 2 pi times this integral. I replaced fx with sine x here. And there are two different situations. When n is plus minus 1, we plug it in here. And then we expand this exponential function into cosine x minus plus I sine x. And remember, this integral of a odd function is always 0 when you have the lower limit and upper limit being opposite to each other. Therefore, the integral of sine x times cosine x is 0. We just need to evaluate the integral of this minus plus I times sine x squared. Sine x squared is this. We can prove this in a different video. And the integral of this part is 0. So what about the integral of cosine 2x? It's also 0 because the integral of cosine 2x is sine 2x over 2. Both sine 2 pi and sine -2 pi is 0. Therefore, we have only one non-zero term, which is minus plus I times half from -pi to positive pi. Therefore, the value of this integral is minus plus I times half times 2 pi. And then divided by 2 pi, we get the final value of a plus minus 1 is minus plus I over 2. What if n is different from positive or negative 1? Well, that's simpler. So we evaluate this same integral, and again, the integral of sine x times cosine nx is 0 because this product is an order function. And now we just need to look at sine x times sine nx, and we take this negative I out of the integral. Sine x times sine nx can be expressed as the difference between two cosine functions here, and minus 1 here and plus 1 here. And then we integrate those two cosine functions, we get two sine functions. And again, we plug in the values of x, we get 0 here and 0 here. Regardless of the sign of x, the sine function of an integer multiple of pi is 0. So we have 0 minus 0 here, 0 minus 0 here, overall is 0. Therefore, we have only two non-zero terms, this two, in this infinite series. And we have the coefficients of this two, negative I over 2 in front of e to the power of ix, and I over 2 in front of e to the power of negative ix. We can simplify this. We got this sine x back in the end. Therefore, the expressions of this a sub n is verified for sine x. Example 2, cosine 2x. Similarly, a sub n is 1 over 2 pi times the integral of cosine 2x times e to the power of negative inx dx. And then if n equals plus minus 2, similarly, we evaluate this integral. We expand this e to the power of plus minus 2ix, and again, the integral of the order function is 0 if the lower limit and upper limit are opposite to each other. And this cosine 2x squared is this. We'll prove this in a different video. And the integral of cosine 4x is sine 4x over 4. If we plug in negative pi and pi, the sine function is 0. Therefore, the result is simply 1 over 2 pi times 1 over 2 times 2 pi, which is just 1 over 2. What if n is different from plus minus 2? The result will be 0. We'll do this derivation, or do it here, and the product of two cosine functions can be expressed in this form: cosine n minus 2x plus cosine n plus 2x. And then we integrate this to cosine function, we get sine functions. Again, sine functions of an integer multiple of pi or negative pi is 0. Therefore, we get 0 here. So similarly, for cosine 2x, the infinite series of its Fourier transform contains only two non-zero terms, the a plus 2 term and the a minus 2 term. Therefore, the result is very simple. This is just the Fourier transform of cosine 2x. We can verify this by plugging the values of a2 and a minus 2. And then we simplify this. We actually get cosine 2x. And therefore, this expression is verified again for this particular example. Finally, fx equals x. This is more complicated. So first, when n is 0, and then we have this a sub 0 equals 1 over 2 pi times the integral of x times e to the power of 0x. And then we just need to evaluate this. X is an order function. The result is going to be 0. Therefore, it tells us a sub 0 is 0. This term is missing. What if n is non-zero and even? When n is non-zero and even, again, we evaluate this, and we take out this negative in out of the integral, and also multiply this x by negative in, and we have the integral of this to be e to the power of negative inx. And now we have to evaluate this integral. This is a little tricky, but remember the product rule. The exact differential of fg equals fdg plus gdf. Imagine this is f, this is g, so this is fdg equals dfg minus gdf. So we have integral of dfg, which is just fg, and we have this integral of gdf here. All right, so from here to here, we used the product rule. And then it's fairly easy to evaluate this part because this is simply 0. If you look at e to the power of negative I n pi versus e to the power of negative I n pi, they are exactly the same, because if you take the ratio between e to the power of I n pi and e to the power of negative I n pi, you get e to the power of I n 2 pi. E to the power of I n 2 pi is 1. Therefore, it doesn't matter if you plug in pi or negative pi, you get the same value here. Actually, it's just 1. So if you integrate this, it's going to be 1 minus 1. All right, how about this part? Again, when n is an even number, e to the power of plus minus I n x is 1. If n is even number, and sorry, I missed this, x equals either pi or negative pi. So just imagine you are evaluating e to the power of plus 2 pi I, or negative 2 pi I, or negative 4 pi I, negative 6 pi I, or positive 6 pi I. The result is simply just 1. All right, so we have this. This part is always 1, regardless of the value of x, regardless of the sign of x. So if x equals pi or x equals negative pi, this part equals 1 anyway. Therefore, we're just evaluating this x times 1 from negative pi to pi. The result is 2 pi. And then 2 pi times this part, we get I over n here. Because 1 over negative I is I, and then 2 pi over 2 pi cancel. All right, so what if this n is odd and x equals pi or negative pi? In this case, this e to the power plus minus I n x equals negative 1. So really just imagine e to the power plus minus 1 I pi, 3 I pi, 5 I pi. They have the same value, which is just cosine pi, or cosine 3 pi, or cosine 5 pi, which is 1. How about cosine negative pi, negative 3 pi, negative 5 pi? They're also the same, negative 1. Therefore, this a sub n, again, we use this expression. This part will cancel because, again, this value is negative 1 anyway. And over here, this value is negative 1. Therefore, we have a negative sign here in red. And then the result is negative I over n for a sub n. So this is important. When n is an even number, a sub n is I over n. When n is an odd number, a sub n is negative I over n. So it's a little tricky to expand x. X, again, is an infinite series of this exponential function. And because of the difference of the sign, I used negative 1 to the power of n here. This ensures that when n is even number, you have I over n. When n is odd number, you have negative I over n. And I excluded this n equals 0 term, because when n equals 0, I think we proved this a sub 0 is 0. All right. Now we're going to separate this into two infinite series. One is from negative infinity to negative 1. The other is from 1 to positive infinity. And because this n here appears here and appears here, we can substitute this n to be negative m. And then m is from 1 to infinity. We have negative 1 to the power of m. This is going to be I over negative m, and this is going to be e to the power of negative imx. And then we replace m with n, and we get this formula here. So really, if you just, or you can just directly change the sign of n if you want to. Again, because n is a dummy variable, so we have this guy. The reason is we want to combine this to infinite series. So now we have this both infinite series from 1 to infinity, therefore we can combine them. and we have this e to the power of negative ix minus e to the power of ix. We have minus 1 to the power of m plus 1 here, over here, and then over here we introduce a negative sign here, and we change this n to n plus 1. And what about this? This part is simply negative 2i sine nx due to Euler's formula, and negative 2i times I is simply positive 2. So this is our simplified expression here, and if we expand it, it's just 2 times sine x over 1 minus sine 2x over 2 plus sine 3x over 3 minus sine 4x over 4 plus sine 5x over 5 minus sine 6 over 6, and so on. The reason I expand this x in this form is because now we can try to verify this numerically. So you can try x equals 1/2 of pi, and then you can use Excel to compute this part. It's very simple because sine 1/2 of pi is 1, sine 2 times 1/2 of pi is 0, sine 3 times 1/2 of pi is negative 1, this is 0, and then sine 5 times 1/2 of pi is plus 1. So really you have just 2 times an infinite series in which you have 1 minus 1/3 plus 1/5 minus 1/7 and so on. So if you use Excel spreadsheet, you can sum up all those terms, and if you do 1,000 terms, the result of this after you plug in x equals 1/2 of pi is 1.570296, and this is actually 99.97% of 1/2 of pi. And actually I can show you the Excel I made. Again, you have n equals 1357. What about the even numbers? Those terms are just 0 when you plug in x equals 1/2 of pi. And then we have this odd terms, which is simply just 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 and so on. So over here I summed up 1,000 terms and then multiplied by 2. I got this numerical value, and this numerical value divided by 1/2 of pi, we get 99.97%.